Hello. And I would say good morning because it's morning for me right now, but who knows what time it is for you. And look at this really cool little periodic table that I have. It's actually a flash drive, little hard drive there. I think you can slide it out maybe. Anyway, this was a gift from the University of Tennessee, Knoxville, so shout out to the Department of Chemistry there for that. But we're going to be using this cute little periodic table to talk about periodic trends. And this is beyond the chemical properties by which the periodic table was originally laid out by Mendeleev and Meyer and others. You know, a lot of people worked on the periodic table, the best way to display all the elements, and there are other forms of it, other ways to display it. But of course, this is the widely accepted one, which is a good thing. We don't want to get too confused. And I did want to point out how especially good this one is because it goes all the way up to element 118. So this is an updated one. A lot of times when you find a periodic table, it's a few years old, and here they're just unnamed with just placeholder names. So we'll be referring to the periodic table as we go through these concepts. And in order to fully understand and appreciate periodic trends, and the ones that are really significant, such as the trend of atomic radius, there's also the trend of ionization energy, and there are others. But we do need to have a starting point, so let me put this over here for now, or maybe over here. Okay. And we will begin talking about this overall. Overall concept, periodic trends. But there is something we should talk about first before we just dive in and say what the trends are. We want to understand why they happen. And to go in that direction, I want to talk about something called shielding. And this is something that's happening within atoms. And so we will review a little bit the structure of the atom from the most fundamental, basic viewpoint. So those of you who have learned more details about specific orbitals, SP, DF orbitals, we're not going to be looking at it from that point of view. We're going to be looking at it more generally. So I can make a more advanced video that brings in all the details of orbitals and exceptions and anomalies and things like that. But today I want to be starting at a beginning general chemistry viewpoint. And we are essentially first off acknowledging that there is attraction that is between a proton and an electron. So let's say this over here. Because all of this will be based on this fundamental concept that when we have a proton in a nucleus and an electron in the atom, that there is a Coulombic attraction here, an electrostatic attraction. And this attractive force is related to the magnitude of the charge, so how many protons you have in the nucleus, and the electron, and then how strongly it's attracted to it. So if there is a larger positive charge in the nucleus that the electron detects, there will be a stronger attraction. Also, another thing that causes changes in the attractive force is the distance between the two. When these are closer together, the stronger the attractive force. But if we increase the distance and we bring the electron out here, it will be a weaker force. Okay, so all of that is related to something called Coulomb's law, but we don't need to write out the formula or do any calculations. We just want to know these concepts. So the stronger attraction comes from those two things. Okay, so if there's larger magnitude of positive charge in the nucleus, that the electrons, I'm going to say feel, I'm going to pretend like they're sentient beings. You could also say detect if you wanted to be more scientific. Or if we say that there is a shorter distance, between those two charged particles. And protons in the nucleus and the electron. Okay. So we'll be basing our discussion on this idea here and talking about this concept of shielding. So let's use a couple elements here in this example. And how about we compare boron and carbon? Let's compare these two elements. They're right next to each other on the periodic table. And we're going to draw out, look at boron versus carbon, but first let's draw out the boron. So what we want to look at is essentially a sketch, a kind of cartoon sketch of the number of protons we have in the nucleus, which boron is element 5. Its atomic number is 5, so there will be 5 protons here in the nucleus. Yes, there are also neutrons, but we're not going to talk about the neutrons right now since they're not charged. So we're just going to be looking at things that affect the attractive forces. Okay, what about electrons? All right. Well, on a periodic table, each of these rows, which we call a period. Each of these periods represents one main shell. Okay, there are also subshells, but each one of these we're looking at a shell. And so this inner shell, you can actually count by how many elements exist there and know how many electrons are in that first shell. So you can, from the most basic point of view, you can imagine that these are somewhat like orbits, kind of like a solar system model. That is not how an atom exists. Our best understanding with quantum mechanics is quite different than this, and very, very fascinating. But fortunately, we can use this model, and it explains the periodic trends that we're going to be getting to. So in this first shell, there are 2 electrons. Okay, and I'm just distributing them randomly. And this first shell only ever holds 2 electrons. And again, we see that represented with this first period having 2 elements in it. Hydrogen having 1 electron, helium having 2. And by the time you get to lithium, there's no more room in that first shell. So it needs to create another shell. And the second shell we'll draw again. We'll draw it like a circle. Okay. And boron has 1, 2, 3 electrons in that second shell. So we can put these around wherever we want. I'm just distributing them. Okay. So this concept of shielding has to do with an inner shell blocking an outer shell electron from feeling or detecting all of the positive charge in the nucleus. So you can almost think of this as a barrier or truly a shield. So for once, the name was chosen to actually represent what they're talking about, which is always nice. Okay, so if you imagine this negative charge here is blocking this electron from 100% feeling all the positive charges here. Because this is negative 1, and each proton is positive 1. You can imagine that this negative charge here can almost negate one of those positive charges. Same with this electron. So we have this inner shell, and by the way, these are called any of the inner electrons. These are called core. Core electrons. Those are any of the electrons that are inside of the outermost shell. The outermost shell electrons, make sure this is showing. The outermost shell, these are the valence electrons. Always the outermost shell, and only the outermost shell. Okay, so these valence electrons, they are blocked from being able to detect the full force, the full positive charge of that nucleus. And we can actually do a rough calculation of this. where we can say, all right, the full positive charge here, the full nucleus, the number of protons equals the atomic number, Z. And then we've got these core electrons blocking the outer electrons from feeling this. And we have two of them. We can call these the shielders. All the core electrons are shielding these outer electrons. So the positive charge that these outer electrons detect will always be less than the actual charge. And there's a name for that. And that is the effective nuclear charge. Okay, the effective nuclear charge. We're going to be talking about effective nuclear charge a lot, so. The symbol for effective nuclear charge is capital Z, and oftentimes subscript EFF for effective. But I will say that there's some textbooks that call it Z star. Okay, I'm going to be calling it ZFF. Alright, so the effective nuclear charge then can be calculated by taking the number of protons, or in other words, the atomic number, of protons, and subtracting out what is known as the shielding constant. But the shielding constant can be approximated by saying it's the number of core electrons. You can do some more detailed calculations by actually distinguishing between different core electrons. You can also look at the effect of different valence electrons shielding each other a little bit, and you can get into fractions and all of that. But the good news is this approximation allows you to fully make predictions of periodic trends on your periodic table. So this is quite lovely to have it simplified in this way, and then allows us, for whatever atom we have, to estimate what that effective nuclear charge is. So we're going to be doing that for boron versus carbon. So let's draw carbon here. This a little bit. Okay, we got our boron. Carbon is right next to boron on the periodic table. So instead of 5 protons in the nucleus, now we have 6. But similar to boron, we've got this inner shell and outer shell, and we can put in our electrons. We've got our core electrons, those 2, and then for our outer shell carbon has 1, 2, 3, 4. And it's in group 4A, which is not coincidental. We have those 4 electrons. Each group, you're adding another electron. So I'm just putting these 4 anywhere. It doesn't really matter where. Okay. So let's calculate the effective nuclear charge for each of these atoms. Okay, so for boron, let's see, where do I want to do it? I don't have enough room here. I guess I'll do it down here below. Effective nuclear charge for boron. We start with the atomic number of protons, which for boron is 5. We subtract out our shielding constant for boron. It's just we'll look at these 2 core electrons. So we end up with 3. And I do like to write +3 here just to remind me that it is a positive 3 charge that the valence electron is feeling from the nucleus. Okay, so let's actually, I want to write that down here. Okay, the effective nuclear charge. Okay, so this is the positive charge that, and we are going to be looking at it from the point of view of valence electrons. It's usually what you do. Electron. And I'll use the word detects. Nucleus. Okay, so in boron, valence electrons are detecting a +3, they're not detecting the full 5. What about for carbon, for a carbon atom? Effective nuclear charge is now 6. Protons minus those core electrons, and there are 2 of them. So it is now 4. These outer electrons, these valence electrons, detecting +4 in carbon. That's a decent jump up from 3. So we now have an increased attraction. Remember what we said early on in the video? We talked about the stronger attraction. If there is a larger positive charge that the electrons feel, that is going to be one of the effects. Okay, there are these 2 effects. Well, what happens when an electron feels that stronger charge? It will be attracted and it will be pulled in. And so we have this larger effective nuclear charge results in this stronger pull interaction, okay, between the protons and the electrons. And the electrons can actually be pulled in and get closer. So the electrons then move closer to the nucleus. Now there is a limit to how close they can get, because there is electron-electron repulsion. So it's not like they can all squeeze in really close, because at some point they will repel each other too much to be able to get too close. But there will be a stronger pull, and they will move in closer. And ultimately, what happens is that the overall radius or diameter of the atom gets smaller. So, this is really, really interesting if you think about this. The radius is smaller for carbon, even though carbon has more protons and more electrons. Carbon is, you could say, in terms of mass, or in terms of number of things you've added one more proton as compared to boron, you've added one more electron as compared to boron, and yet it is smaller. And this is all because of effective nuclear charge and it being greater. That causes this decrease in the atomic radius. So whenever you're looking at these periodic trends, and in this video we're only talking about radius right now, but we're going to see this with other trends. Going across a period, we see increasing effective nuclear charge. And so generally, starting at one end, going to the other, you see a decrease in atomic radius. Very counterintuitive. You would imagine as you add protons, it get larger and larger. So whenever you are trying to explain what is this difference in radius as you go, say, from indium to tin or something, why is that getting smaller? Your answer is not, oh, because tin is to the right on the periodic table. There you're just acknowledging what the trend is. The explanation as to why is because it has a greater effective nuclear charge. So whenever you're explaining, you'll want to bring in effective nuclear charge when you're talking about going across a period. Now, going down a group is a little bit different, and I will end on that. And let's compare, since we just drew carbon here, let's look at what's directly below carbon on the periodic table. Right below carbon, silicon. So if we were to draw a sketch of silicon atom using the same simplistic view, but it still works to show this concept. Silicon now has, and we can actually see how many protons would silicon have. So we're here with carbon that has 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. Now on most periodic tables you would see atomic number 14 there. You can just go with that. Okay. So we've got our 14, and I don't think I'm going to draw 14 little protons, but instead I can say, hey, here's our nucleus. There are 14 protons. All right. And we have, as always, our innermost shell that holds the 2 electrons. We have the next shell that holds 8, which we can see 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons are held in that second shell, but silicon is in a third shell. So we need another one. So as you can see, just like layers of an onion, silicon has a whole nother shell than carbon does. So if we wanted to put in our electrons, we could, and there would be 8 here, right? And then the 4 electrons that we have for silicon would be out here. So we have added a complete another shell. And so silicon will be larger than carbon because of this addition. Now, the way I drew it, because I didn't have enough room, it looks about the same size, doesn't it? But if I were to draw carbon with the same distance here, then it would look smaller. Okay. So, our overall trend, and I love this because there's no exceptions to this, is that if we go down a group, atomic radius, always larger. Okay, and this is due to adding shells. We just need to make sure I have enough room. So in this case, this trend, it's not due to effective nuclear charge. It's due to these just physical space, adding a whole nother shell of electrons. Those electrons are also repelling each other. Okay, all of that. Meanwhile, draw this here. Our trend as you go across a period. This is overall generally, well, I'm saying size, but radius decreases. And notice notice that this is overall. There are small exceptions. There's some little glitches that you see here and there, little jumps. Okay, but overall, you see a decrease due to the increase in the effective nuclear charge as you go across the period. Okay. So, this was shielding and effective nuclear charge as it applies to atomic radius. We also see periodic trends with ionization energies, and those are also related to the increasing effective nuclear charge across a period. But we don't have time to talk about ionization energy in this video, but that will be a good topic for a future video. Alright, and thank you, as always, for the requests. I have some requests for more organic chemistry, so I'll be doing more of that, and some more calculations. So thank you, as always. Don't forget to subscribe so you find out when I have more videos coming out. And keep those comments coming. I love them. You guys are awesome. So thank you, and I will see you again real soon.